Welcome to this course by RouteFabric. In today's session, we're going to be working in RStudio and writing code to walk through a fairly simple case study as an example of a data science workflow that we have described in other sessions. The data set that I'll be reading in today is a sample credit card data set. So the context for this data set is fraud detection. As you know, credit card companies in our modern day are constantly battling fraud, and fraud doesn't happen very often. It's usually less than a percent of the time that a credit card transaction is someone trying to commit fraud, but it does happen, and it costs these companies a lot of money. So machine learning is a effective tool that many organizations are using today to help detect when someone is trying to make a payment with a fraudulent credit card or a stolen credit card. And the data set that we'll be using today is a prepared, summarized data set that contains a set of transactions as well as a subset of those that have been flagged as fraudulent. So I'm going to read in this data. Oh, and I did not initialize my libraries. I'm going to read in this data, and then we'll take a look at it. R has a really nifty function called glimpse, which is my preferred way to get a first look at a data set. So let's take a look here. Glimpse kind of rotates the data so that you can see the variables along the left side here, and then you just get a glimpse as to what each of these columns contain. So it looks like there's a time column that is some standardized measure of probably date information. And then there are variables 1 through, it looks like, 28. These variables, we don't know anything about them. And that's the nature of publicized data. This credit card data is real, and it came from an actual credit card processor, but the data has been highly processed and obfuscated so that the public can work on it without risk of sharing anything sensitive from that company. So there's these 27 variables, they are 28 variables, they've just been labeled V and then a number. So we don't know anything about them other than what we can see, which is that they are all numeric, they're all decimal point values here, and we'll take a look more closely at sort of those distributions and other things in just a moment here. Looks like we also have an amount column that contains probably the amount of the transaction. Those look like dollar amounts of payments made on a credit card. And then most importantly, this variable down here, the class variable, is our outcome. That's the was it a fraudulent transaction or not column. So just to give you an idea, that class column, we can use this table function to see that nearly all of those transactions were good transactions, but about 500 of them, 492, have been flagged as fraudulent transactions. So our goal today is going to be using this data set. We're going to try to build a model that effectively predicts which of those, which of the many transactions, which of the approximately 285,000 transactions were fraudulent, and so that we could use that model in the future to try to catch fraud in the future. Okay, as I mentioned, let's just take a look using the summary function, which is a very basic function. We can just look at and sort of get a glimpse of all of this data. You can see our variables that we looked through before, V1 through V28. And this gives you a high-level idea of kind of how this data has been arranged and processed. Specifically, all of the columns, all the variable columns have been standardized such that their mean is 0. It is a very common practice in data science and preparing a standardized data set, and it's not especially surprising. But again, we don't know much about this data set other than that it has been standardized. You'll also notice that the range of these variables is relatively constrained. It does look like it has been, these are essentially z-scores probably, of these various variables, because they're going from a negative to approximately the same amount positive. Not all of them, but many of them go from negative 24 to positive 23, and with a mean of 0. So there has been some good solid processing done and preparation done on these variables, and this is often the case when we're using sample data sets. The cleaning of this data set took a very long time, and some nice person at a credit card processing company, or maybe a nice team, did that for us, so we don't have to worry about that. Okay, I also like to, rather than just looking at these summary statistics, I do like to see the distributions in graphical form. It's a nice thing just to visually look at the data, and when there's only a handful, maybe 20 columns here that we really need to look at, that's an easy way to get a quick sense for what this data set contains. So I'm going to be operating in all of my code today within the kind of TidyVerse paradigm. And if you don't know what that is, you can check out our other courses on RouteFabric. The TidyVerse paradigm, TidyVerse itself is a collection of packages that are intended to work together and sort of use the same coding vocabulary. And so you'll see me using things like select, and in this case, starts with the letter V. And you'll see what that does is it shows us, pull this down a little bit, this gives us a quick preview. It's selecting everything that starts with V and nothing else. So these operators are available within the suite of packages here called the TidyVerse, and that's a topic for another day because that's outside the scope of today's discussion. I'm also going to use a command called gather, which is going to take this data set from wide, which is what it is currently right now, and I'm going to gather it into essentially key value pairs, where I'm going to call my variables features and then the values that they contain. I'm going to call values. I'll just execute that so you can see basically what it's done is it's taken the data set from a variable per column, and then the values contained in the cells of that table, and we've now gathered it into a very long format. So now we have almost 8 million rows by just 2 columns, and those columns are the feature and the value contained within that feature. And the only reason that we do this isn't very conducive to modeling, but it does make it very easy to plot and compare some distributions and other things like that. So I'm going to not explain very heavily what I'm doing here with the ggplot visualization tool, but basically what I'm saying is I want to look at the distributions of the values in this value column. I'm going to ask for histograms, just so I can get a quick visual look at what this kind of looks like. And then just to make it a little easier to look at, I'm going to use this facet wrap function, which I will demonstrate what that does in just a moment. We need to make the scales free, so because not all of our variables are on the same scale. And then just to make it a little cleaner to look at, I'm going to use the minimal theme, which is what I typically do. Okay, so this ggplot command and then the subsequent additional layers that I'm adding with these plus symbols, these 4 lines of code are going to build a nice visualization for me. And again, ggplot and all of its intricacies are outside the scope of today's discussion. But when I execute this, it is going to go and assemble histograms for each of the categories of the data that I had pulled to long format. So we've got features, V1 through all the way down to V28. We've got the values that are within those features, and this is, of course, too small to see. We'll look at it more closely here. Give it a second to re-render. what we have now is the distributions of all of our variables. They haven't been ordered very nicely, as you can see, but we do get a sense for how some things are distributed. Many of them, as you can see, are sort of centered around 0. A lot of them have a lot of frequency on that 0 value, and then some of them are quite spread. Or excuse me, some of them, like these over here, are a little bit more normal and a little more comforting. Some of them are quite skewed, where 0 appears to be about the max, and then V1 goes all the way down to a -60. Anyway, again, we don't know a whole lot about these variables, so there's not much I can conclude in this particular example, just because I don't know about these variables. But if this was a real data science project that I had more ownership over, I would know what these variables were. I would be able to look for red flags. I'd be able to examine what these distributions are doing and see if there's anything that makes me nervous, or otherwise that I want to go back and do some additional cleaning or data prep on. So that's just an example of one of the ways that I'm looking and sort of visualizing and exploring data sets. Another thing that I often like to look at is just intercorrelations among the various variables. So we're going to use the core function to get some Pearson correlations. Oops, you have to spell Pearson right, or Mr. Pearson might not like us. So that's now calculated all of those intercorrelations. And then I'm going to use a nice function called core plot, which is available to me because I have installed that library. This is not native to R, but it is a very useful way to quickly get an idea of whether there's really high correlations. I like to look at them as squares, which I'll show you in just a minute. Oh, and then nobody likes red text. That is very ugly, so we're going to make it black. So it's a little easier to look at. So this plot, after it re-renders, there we go, provides us just a really high-level idea of how correlated these variables are with each other. So we've got each of the variables listed along the top and along the side. This is a correlation matrix that's also got some coded information in kind of the darkness and the shading of these squares. So you can see anything that's highly blue, which of course each variable with itself is very, very dark blue because it's correlated perfectly with itself. But it would be potentially problematic depending on the method that we decide to use. It might be potentially problematic if a lot of the variables, if say V9 was very highly correlated with V12, for example. But you can see there's very little color in this matrix here, and amount appears to be correlated with a few of the variables, and that's okay, not too bad. But the actual predictor variables, V1 through V28, there's a lot of white in here, and that is comforting for the most part because we don't want to have redundant information. As it turns out, the sample data set that we're using has probably been manipulated so that they've already removed all of the kind of redundant and overlapping variants in the various variables. Probably a PCA analysis, principal components analysis, that has reduced the number of features to these 28. I am guessing, but that is a probable scenario. Okay, so we feel pretty good about the correlations. We are, the last thing I want to check, as I've talked about in other sessions here on RouteFabric, I also want to get an idea of the missingness in the data. And because this is a sample data set, this won't be a very great example because dummy data sets like these very seldom have missing data because they've already been kind of cleaned up for us. But I do want to give you a sense for what you can do to just get to get a glimpse of whether there is missingness. Now this Missingness Map function, this mismap function, will go and it'll basically look at missingness across your entire data set. With a relatively large data set here, that can take a very long time to process. And so often with this Missingness Map, I'll do what's called downsampling, and basically I'm saying with a handy function from the TidyVerse, I'm saying that I want to take 10% or 0.1 a proportion of 0.1 of this data and feed that into this function rather than doing this function on the whole thing. So that'll just make processing time a little bit faster. I'll execute that and you'll see that my computer will churn for a minute even at just 10%. It'll take a minute for it to populate this plot over here. But basically what it's going to do is provide a little map of each of the observations in the at least 10% of the data set that's remaining, and anything that is where there's a value missing, it would be marked as blue, and then anything where it's not would be marked as red, and of course, as you can see, it's very red. And again, this is a dummy data set, and we might expect this when a data set has been highly processed and sort of prepared for example analyses like these. But that is something that you typically want to look at. With real-world data, there's going to be lots of missingness, and those are things that we would have to account for. And this Missingness Map is a nice way to explore that. Okay, so those are some of the steps that I might go through to kind of familiarize myself with the data, to prepare the data for analysis, and to just kind of understand how the data is arranged and maybe any patterns that might be in there. And having done all of those various activities, and in a real-world situation, I might do quite a few more. In this case, I'm feeling pretty good about the data. So we are going to go ahead into our machine learning modeling. When we build a model, it's a really good idea to try to simulate how a model might behave on unobserved data. In other words, to use some but not all of the data to train a model and to teach the machine how to catch, in this case, fraud as the outcome of interest. And it's a good idea to do that on a subset of the data and then try to use that model to find fraud in other data that the model hasn't seen yet and hasn't been trained on. It's a very common practice in data science. And typically how that works is we're going to establish a training data set that's a subset of our credit data frame here. And again, I'm going to use that handy sample fraction function from the TidyVerse. And common, you can sort of do what makes sense for you, but very common is a 70-30 split. So I'm going to train my data on 70% of this credit data frame. It's going to be my training data set. And then I'm going to use the test data frame to test that model's performance. And there's a wide variety of ways that you can do this, but I'm just going to use this anti-join from the TidyVerse that is convenient, where basically it's saying, give me from credit data, give me all of the data that is not found in the trained data. Oh, and guess what I forgot? I forgot that this credit data, if you look at it real quick, it actually doesn't really have what we might consider a primary key, which I should have added up here, and I'm going to go ahead and do that. What I mean is there's no way for the data frame to do a join operation because there's no joining key that allows us to uniquely identify each row. So I'm just going to add a key column here that is derived from the row number. So they're automatically unique. And just because I like to have my keys as the first column, just by convention, I'm going to also do that. So what this has done is I've gone into credit data. I'm mutating or adding a variable. That's TidyVerse language for add a variable. I'm going to call that variable key, and I'm going to derive it from the row number. So if I add that, and then I'm just reordering the columns here. Select is a way to say choose which columns you want in which order. And so I'm saying give me the key column first, and then everything else after that. What this does is it's given me a key column, and you'll see that those keys, that's full unique, and it'll be numbered from 1 to 284,000. And then the rest of the columns have been arranged thereafter. So I've now applied that to my credit data frame, And we can come back here, do our sample fraction to get 70% of that. Our train now has a key. And you'll notice that these are just randomly chosen rows based on this random distribution from the sample frac function. This training set now has about 200,000 rows in it, which is 70% of our full data set. And then we'll do this anti-join on credit data and include everything that is not in that training data as defined by the key column. That's how this function works. So now our test data has about 85,000. One way to just double check that that all worked would be to say, give me the number of rows of that train data set, and I'm going to divide it by the number of rows of our original. And that gives us a fraction of 0.7, proportion of 0.7, which is exactly what we want. Now, one thing that's usually a good idea to test is to make sure that nothing weird happened with our outcome variable. Our outcome variable, if you remember, was called class. And there's this table function that will allow us to say, in that training data set, that class variable, let's look at the distribution or the frequency of the ones as compared to the zeros. And we can do the same for the test data set. And it's actually kind of hard to compare these numbers. So what I typically do here is I will then divide that by the number of rows in the respective data sets. And that will allow us to just compare the proportions. Now, obviously, these proportions are very small, so it's a little hard actually to judge whether that's right. It's basically 0.1% of each of the data sets are failures or fraudulent transactions. That looks about right, 0.998 and 0.998 on both sides. We can be confident that our split here, where we took a 70-30 split, did not unfairly advantage the training or the test group. It was truly random, and that's just a thing that I usually like to check just to make sure. All right, lastly, we are going to now build a model. We're going to use the training data, that 70% of that data, to build a model. And there's a variety of algorithms we could choose for the sake of convenience, and just because we're using a simple example here, I am going to use the general linear model and build a regression. Now, the kind of regression that we need to use, because our outcome variable, remember, is a binary true-false flag called class, we're going to use logistic regression, or a binomial assumption within our regression. And the way that the GLM function works is you tell it the outcome, and then I could, if I wanted to, I could list out, this is basically saying class is being predicted by, I want to predict class by using the variables v1 plus v2, and I could write out all of these individually, and that would be very time-consuming and rather annoying. Or as a shortcut, you can say, give me the outcome regressed on everything. That's what that dot summarizes. You need to tell it what data to use. And in this case, of course, we're going to use our training data. But rather than, if you remember, our training data includes our variables of interest, so v1 through v28. It also includes amount, and that's probably okay to try to include in the distribution to account for the transaction amount. Class is our outcome, but there's also the time and key variables that are probably not something that we want to predict with. This is just a join key that we had, and I don't know what time is. I don't know that it's something that's valid to have in the model. So just to be safe, I'm actually going to, on the fly here, remove those two variables so that they're not considered within this GLM that we're setting up. So now what this is going to do is it's going to try to predict the class variable on all of the variables in the data set, but that data set has had a couple of them removed. Hopefully that makes sense. In fact, we can get a little preview of what this looks like. This is the actual data set that will be passed into the GLM function, And you can see it's got variables v1 all the way through v28, as well as amount, and then that outcome variable. Perfect. And then again, because we're doing logistic regression, we need to call out and instruct the GLM to use the binomial distinction here. Okay, now I'm going to go ahead and execute this. Now the computer is going through, it's using the training data. We're teaching the computer right now how to identify the ones, or the failures, the fraudulent transactions, as defined in this column, given the information available in v1 through v28. And you can see that that was quite fast. Data set is not huge, and logistic regression is a relatively computationally efficient. So just as a summary, we'll just look at the results of this model. What we've got here is a very standard model output that allows us to say, as we are predicting that class variable, we used the information available within each of these features, and you can see that just based on how regression works, it is providing an estimate or a weight on each of these variables, and then it's doing some calculations to decide how influential or how likely this variable is to show a relationship that's not due to chance. That's what these stars are indicating. This is getting a little statistics heavy, and we won't get too far into the weeds. But basically, there's some variables with 3 stars, and that, among other things, is a bit of an indication that, for example, v20 and v21 in this particular setup of this model, they have an effect on whether something might be considered fraudulent or not. So this is a summary of what's happening in this logistic regression. Of course, understanding the nuances of a logistic regression and all of the features and the way that we might validate this model is going to be outside of the scope of our discussion today. But we can take a look at sort of the underlying weights on the various variables. Okay. Having looked at the summary of the model results, again, that was just the summary of performance and the weightings and the different variables that went into the model based on our training data set. Ideally, we'd like to use the information within that training data to predict and catch fraud on data that we haven't seen yet. We can simulate that by applying the parameters that were achieved during the model training here, applying those parameters and score or get predictions for the test data. So if you remember, we have this test data set that had 85,000 or so of the data. This data has not been seen by our model yet. So this is a blind holdout or a holdout sample that we are going to evaluate the performance of this model on. So to do that, we're going to use the predict function, which allows us to specify that GLM fit object, which is just the result of our model training. We're going to apply it to the test data set. And in so doing, we get a number of predictions out. This is not very pretty to look at, so but basically we've gotten a number of probabilities because this is a logistic regression from 0 to 1. So if we now look at that in a confusion matrix, we're just going to build a table based on the test data's actual outcome, which is the class column, if you remember. And then that prediction. And when it comes to logistic regression, what we have to do is choose some threshold, not 0.05, 0.5. The predictions here that are, let's actually just look at our predictions. Basically, they go from 0 to 1, and these are probabilities where 0 is, given what we know from the model, we are trying to predict whether a given observation in this data set is likely to be a fraudulent transaction. And our model has scored each of those rows according to this, according to that model, giving it a probability of between 0 and 1. Now we can choose to say anything above a 0.5, we will classify that as fraud and we'll flag it as a fraudulent transaction, and then the hypothetical organization can prevent the transaction or stop it or otherwise investigate the possible fraud. This 0.5 probability cutoff is just chosen by convention, and it can actually be changed depending on your scenario. It may make sense to have a threshold of 0.6 or 0.3. It just depends on your scenario. But typically, by default, we choose 0.5. So basically, we're saying, show me which of the actual outcomes that we know about, which are is that class column. There's some, if you remember. In fact, let's just look at it. There's 135 ones in here, or failures, or actual fraudulent transactions in this test data set. What we're trying to see is how well our model predicted that those 135 were actually fraud. So we're going to create that confusion matrix table. And the result is, it's a little cryptic to read in this format, but basically this 0 and 1 are the 0 and 1 from our class column. And then this true false is the result of asking the question of these predictions, is the given prediction above 0.5? And of course, some of them are, because our distribution goes from 0 to 1. So if we choose a cutoff of 0.5 to say, yes, that is a fraudulent transaction, then this will result in true. And what we can see is there are 88 that we predicted with our model. We predicted that those would be fraudulent, and in fact they were. There are 47, however, that we predicted would not be fraudulent because they were below 0.5. And those 47 actually were fraudulent, so we missed those. And that's something that we would try to improve in future iterations with our model. Likewise, we predicted that there were 11 that were fraudulent that actually were not fraudulent, right? Our prediction said that it was above 0.5 likelihood of being fraudulent, but this the class column revealed that we were wrong about those. So depending on the modeling scenario, this 47 and this 11 may be okay, and in many cases it's not. We obviously try to, the ideal best model, perfect model, would be where all the zeros were predicted as zeros or falses in this cell here, and where all the actual 135 ones, the fraudulent failures, we predicted those would all be here. That would be a perfect model, and we would celebrate and be very happy. Very few models are perfect, and this one certainly isn't, because we've missed some and we've flagged some as fraud that weren't actually fraud. So through our next stages in our data science process, we would probably iterate. We might try some different algorithms. We might tune and otherwise try different parameters and different settings within our various algorithms to try to optimize the performance of our model. All right. This tutorial went from beginning not to the end of our data science workflow, because really we haven't really modeled or simulated how an organization might actually use this model, aside from just testing its performance on our test set of data. That's a very small part of the end result of data science. Ideally, if I was working for a credit card company, we would want to very carefully test and validate models like these, and then we would establish them. We would deploy them, rather, and we would make them available to our transaction processing system that would allow us to provide these predictions on new data as new transactions were coming through our processing workflow. And some of those we would want to flag as fraudulent, and that would be the ultimate goal of a data science project like this. But for demonstration purposes, we're going to end there. So I hope this was informative. If you'd like to learn more about data science and using R to accomplish data science, then please check out our other courses at RouteFabric.com. Thank you.